In this video, we're going to talk about what is meant by potable water. Now, potable water just means water that you can drink, drinking water. Now, does it mean pure water? No, it doesn't. Pure water, distilled water, which doesn't have anything dissolved in it, is you wouldn't ever really find it. You wouldn't ever find it naturally. Potable water quite often will have quite a few things dissolved in it, and all these things are actually harmless. So I've taken for an example here is Evian water. Okay, other mineral waters are available. I'm not getting paid anything by Evian for this video, unfortunately, but I'm open to offers. So mineral water has a very similar composition to the water that comes out of the tap in this country. And so here you've got you can't really read the label too well because it's too small. So that's why I've written it down here. But you can see they've got the list of ions that are in it and concentration in milligrams per litre. So we don't really use a litre as the unit. We use decimeters cubed. That's the same volume as a litre, 1,000 centimeters cubed. And a milligram, of course, this one here, 360 milligrams is actually equal to 0.36 of a gram, times it by 1,000. Okay, so you can see in Evian water, you've got quite a bit of calcium and magnesium ions dissolved. That's very common because a lot of rock, of course, is calcium carbonate, limestone, which sometimes has magnesium carbonate. And those compounds are ever so slightly soluble in rainwater, and so they'll end up in the drinking water. Interestingly, here you can see that there's quite a lot of hydrogen carbonate ion, and that is very typical of most drinking waters, and it makes it slightly alkaline. Okay, so you see the pH is 7.2. Rainwater has actually got a pH of about 5.5 because rainwater has got carbon dioxide dissolved in it, which is acidic, and so of course drinking water at the tap will also have CO2 dissolved in it, but it's not acidic because it's got an alkaline substance, the hydrogen carbonate ions, that sort of balance the acidic substance in there, the carbonate, about pH 7.2. Right, let's have a look at sodium ions. Now you can see sodium ions, you have got a small amount of sodium in there. That's okay, but if the sodium ion concentration gets too high, of course the water would taste salty, and A, you wouldn't want to drink it because it wouldn't taste nice, and B, you know, if the sodium ion concentration gets too high, you can't drink it. You know, if you get stuck on a desert island and there's no fresh water, you can't drink seawater. you'll die. Okay, so drinking water with the sodium concentration is too high, you can't drink it, and people won't drink it because it tastes horrible. Potassium, small amounts of potassium in there. You can see that. A little bit of silicate ions, they don't really do much, and sulfate and chloride ions, they're pretty innocuous. Here we've got nitrate ions. Now that is a problem. That level of nitrate is obviously okay, but nitrate, you can't drink tap water, can't drink water if there's too much nitrate in it. It's bad for you, and that is a problem because nitrates come from artificial fertilizers, because of course plants need nitrate to grow, and if too much artificial fertilizer is applied to crops, it rains and it washes off the crops and it ends up in the water table, and there's too much nitrate in that, and it's not good for drinking water. Okay, finally, you'll also see on the bottle there, normally it says this thing dry residue at 180 degrees C. That means when you evaporate all the water, what's left over? And they said at 180 degrees C there because some components will actually undergo thermal decomposition. So for example, at high temperatures, hydrogen carbonate ions will decompose into hydrogen ions, and well, you'll end up getting carbon dioxide, okay, and water. So you lose some of them at higher temperatures. Okay, so those are the typical things that are dissolved in potable water, in drinking water. That's a very typical composition, and I'd say it's because the water has washed over rocks containing calcium carbonate, magnesium carbonate, it dissolves some of them, and that's perfectly okay to drink. So a suitable source of drinking water, obviously it's got to not contain too much sodium, not contain too much nitrate. It doesn't matter if it contains calcium, magnesium. In actual fact, calcium, of course, is you need calcium for bone development, teeth development, so that's not a problem at all. Right, so drinking water, you can't drink it from a reservoir, fresh from a reservoir, because it will contain particles in it. So first of all, it needs to be filtered. Okay, and it's filtered by passing the water onto these very large. These are filter. They're called filter beds. So the water goes on there. You have a layer of larger stones at the top and smaller stones, and finally sand, and all the little solid bits get filtered out. And this would be, so the water coming out here would look clear, but it's still, you can't drink it because it needs to be sterilized. Okay, it would contain microbes. Okay, which may be harmless but may cause disease. Okay, so the microbes need to be removed or killed, and that is usually done by treating the water with chlorine gas. Okay, now chlorine is a pretty powerful oxidizing agent. It will kill any microbes, and before the water gets to your house, it's a gas, so it will evaporate from the water, so it won't get to you. A new way of sterilizing the water is, instead of using chlorine, is to use O3, which is another gas, and that's called ozone. Of course, most oxygen we know is O2. This is O3. It's more reactive, and it's an oxidizing agent. It will kill it's toxic to bacteria. And then if there's a final way of using it, of sterilizing it, which is to shine UV light on the water. Now, the problem with UV light, of course, it's not going to penetrate into the, if you've got very large volumes of water, it won't get into the middle of it, and so it's not suitable for that. Ozone, the problems with that, it's more expensive than using chlorine, but the good thing is the only byproduct, of course, is oxygen, which is harmless. Chlorine, this is the most common way of sterilizing water, is cheap, but it does that people are becoming worried that you end up with some chlorine compounds which may be toxic and build up in the environment and be bad for living organisms. So there's the three ways of sterilizing water, and as I say, chlorine is by far and away the most common method used. Right, now we need to talk about, so that's water in this country. We've got quite a lot of running water. It's not really, we're never short of it, but in certain countries, desert countries, they will not have enough fresh water, and so they have to get seawater and make it drinkable. Now, how's that done? Okay, so seawater contains obviously large amounts of sodium chloride dissolved in it, and that needs to be removed because you can't drink it if it's got that in it. Okay, so the most well, the original way of getting rid of the sodium chloride was by distillation. Now, I'm not going to talk about distillation in detail because that's something we've done lots of times before, but basically the water's boiled, the steam coming off it is cooled down. The sodium chloride, of course, stays in the water. That's not volatile. It doesn't boil with the water, and then you condense the steam, and you'll end up with distilled water, pure water. The problem with this method is very energy intensive. Uses a lot of energy because you've got to boil all of the water that you're making. Okay, so that makes it very expensive. There's another way of doing it, and this diagram down on the left shows you how. This is called reverse osmosis. Now, what you have here is you have the water, and this is supposed to be a kind of a syringe, and so the water is under pressure. You force the water under pressure, and here you have a semi-permeable membrane. Now, a semi-permeable membrane that will allows H2O through it, but it won't allow the sodium ions and the chloride ions, which I've drawn there as those coloured blobs, and they're too large to pass through the pores in the semi-permeable membrane. So all the water coming through here, the water is the red dots that can get through, and what gets left behind is the sodium chloride. Now the advantage of this is it uses much less energy than distillation. But the disadvantage is that the membrane rips sometimes. The membrane will split due to the high pressure that the water's put in, forcing it through that. And if you think about it, it's called reverse osmosis in biology. Remember that if osmosis was occurring here across this semi-permeable membrane, of course, then the water would pass in that direction, wouldn't it? You'd have the water molecules passing from the dilute solution on the right to the concentrated salt solution on the left. But because it's pushed under pressure, it happens the other way. Okay, so that is all we really need to know about potable water. I'm going to refer very briefly to the required practical, because the required practical, all you have to do is distill some water, some tap water, and you boil it, and then you condense it, and you should get some pure water. And then also you measure the dry residue of a sample of water. Okay, so basically you boil it up, and then you measure what mass you got of solid left over afterwards. It doesn't work very well, because if you looked at the Evian water example there, I think it was about, the dry residue there was 360 milligrams or something like that per dm cubed per litre. So that's 0.36 grams in a litre, in a dm cubed of water. You in a practical lesson, you're not going to have time to boil a litre of water away, because it take too long. A whole class of people doing that, right? It's not really. So you've used a smaller amount of it in a measuring in an evaporating basin, and of course then if you only boil 100 centimeters cubed, say, it takes quite a while to boil 100 centimeters cubed, but if you did 100 centimeters cubed, then you'd only end up with 0.036 grams, and you'd hardly be able to measure that accurately after heating up you'd have to get the evaporating basin with 100 centimeters cubed of water, weigh that, then boil it, reweigh it, and it would only be that 0.036 grams heavier than it was at the start. You probably wouldn't even notice that. Okay, so that it's a required practical, but it's not a great experiment. Okay, and the other part of it is just simply distilling some water. Okay, so that is all we're going to say about potable water.